What if everything you've ever touched, every person you've ever loved, every thought you've ever had, was nothing more than light chasing its own tail? What if the solid reality you experience right now is just photons trapped in an endless dance, creating the illusion of matter? I'm about to show you something that will fundamentally change how you see yourself and everything around you. Right now, as you watch this video, you think you're made of atoms. Protons, neutrons, electrons, the building blocks of matter that you learned about in school. But what if I told you that some of the brightest minds in physics are now questioning whether atoms are actually things at all? What if they're just ... light in loops? Here's what will absolutely blow your mind. In 1990, a physicist named Hans Dehmelt at the University of Washington captured a single electron and observed it continuously for 10 months. 10 months of staring at one of the fundamental building blocks of reality. And you know what he couldn't figure out? What it actually is. Because when you look close enough, an electron doesn't behave like a tiny ball of matter. It behaves like a wave of energy that somehow learned to chase itself in circles. And this isn't fringe science. This is the cutting edge of quantum physics, string theory, and our understanding of reality itself. We're talking about Nobel Prize-winning discoveries that suggest everything, your body, this planet, the stars, might just be elaborate knots of light. By the end of this video, you're going to understand why some physicists believe that matter is just frozen light, and what that means for literally everything you thought you knew about existence. And I'm warning you right now, once you see what I'm about to show you, you can't unsee it. Your hand will never feel quite as solid again. But before we dive into this reality-shattering journey, do me a favor. Hit that like button right now, because what you're about to learn took humanity centuries to figure out, and I'm going to compress it into the next few hours for you. Subscribe and turn on notifications, because we're going deep into the nature of reality itself. And drop a comment telling me where you're watching from, and what time it is there right now. I want to see how many people around the world are having their minds blown simultaneously. Are you in Tokyo at 3 a.m., London at dinner time, Los Angeles on your morning commute? Let me know. All right, let's begin. To understand why atoms might be loops of light, we first need to understand what light actually is. And trust me, it's weirder than you think. For most of human history, nobody knew what light was. People thought maybe it was little particles shooting out of our eyes. Then came Isaac Newton in the 1600s, who argued that light was made of particles he called corpuscles. But then other scientists like Christian Huygens said, no, light is a wave. And they fought about this for centuries. Think of it like this. Imagine you're trying to describe water to someone who's never seen it. You could say it's made of individual molecules, little particles. But you could also describe it as waves rippling across a surface. Which is correct? Both, neither. It depends on how you look at it. In 1801, a scientist named Thomas Young performed one of the most important experiments in history, the double-slit experiment. He shined light through two narrow slits and watched what happened on a screen behind them. If light was just particles, you'd expect two bright lines. But instead, he got an interference pattern, alternating light and dark bands, exactly like what happens when water waves overlap and interfere with each other. Light was behaving like a wave. But here's where it gets weird. In 1905, Albert Einstein, that Einstein, showed that light also behaves like particles. He was studying something called the photoelectric effect, where light hitting metal surfaces knocks electrons loose. And the crazy thing was, it didn't matter how bright the light was. What mattered was its frequency. Red light, no matter how intense, wouldn't knock electrons loose. But even dim violet light would. This only made sense if light came in discrete packets of energy, particles called photons. So light is both a wave and a particle. It's both, depending on how you measure it. This is called wave-particle duality, and it's one of the fundamental mysteries of quantum physics. Now here's the first mind-blowing connection. In the 1920s, a French physicist named Louis de Broglie had an absolutely wild idea. He said, if light can be both a wave and a particle, maybe particles can be both a particle and a wave. Maybe electrons, which we thought were tiny balls of matter, also behave like waves. And he was right. Scientists confirmed that electrons create interference patterns just like light does. Electrons, the things that orbit atoms and make up matter, are also waves. Everything at the quantum level has this dual nature. But de Broglie went further. He proposed that an electron in an atom isn't just orbiting like a planet around the sun. Instead, the electron is a wave that wraps around the nucleus. And it can only exist in certain orbits where the wave connects perfectly with itself, where it forms what's called a standing wave. Think of it like a jump rope. You can only make stable patterns when the rope completes full waves. An electron in an atom is like a wave eating its own tail, a loop that has to connect perfectly, or it doesn't exist at all. This is why atoms have discrete energy levels. An electron can't exist halfway between orbits because the wave wouldn't connect with itself properly. It would destructively interfere with itself and disappear. The electron has to form perfect loops. So right from the foundations of quantum mechanics, we have this bizarre idea. The particles that make up atoms are actually waves configured in loops. They're not little balls orbiting a nucleus. They're vibrations that have learned to form closed paths. Now let's talk about the most famous equation in physics. E equals mc. You've seen it. It's on t-shirts, posters, everywhere. But do you actually know what it means? Because understanding this equation is the key to understanding why matter might just be trapped light. E is energy. M is mass, the amount of matter in something. C is the speed of light. And that little squared means you square it. You multiply the speed of light by itself. The speed of light is about 300 million meters per second. So C is an absolutely enormous number. What Einstein's equation tells us is that energy and mass are the same thing. They're convertible. Mass is just a form of energy, and energy can become mass. They're like ice and water. Same substance, different states. Think of it like this. Imagine you have a credit card and cash. They're different forms of the same thing, money. You can convert one to the other. E equals mc says that energy and mass are different forms of the same fundamental stuff, and you can convert between them using the speed of light squared as the conversion rate. Here's what will blow your mind. Because c squared is such a huge number, a tiny amount of mass contains an absolutely colossal amount of energy. 1 kilogram of matter, about 2 pounds, contains enough energy to power a city for years. That's what nuclear power plants tap into. That's what happens in nuclear bombs. Matter is just incredibly dense, compressed energy. But it goes the other way too. Energy can become matter. In particle accelerators, like the Large Hadron Collider in Switzerland, scientists slam photons, particles of pure light, pure energy, together at enormous speeds. And you know what happens? The photons transform into particles of matter. Electrons, quarks, even heavier particles pop into existence from pure light. Light becomes matter. Matter becomes light. They're interchangeable. In 1997, physicists at Stanford's SLAC, National Accelerator Laboratory, performed an experiment called the E144 experiment. They used incredibly intense laser beams and collided them with high-energy electrons. And they successfully created matter from pure light. They watched photons turn into electrons and positrons right before their instruments. Light became matter. This is crucial. If light can become matter and matter can become light, then what's the actual difference between them? Maybe there isn't one. Maybe matter is just light that's somehow become trapped, frozen, locked into a pattern that gives it the properties we call mass and solidity. Here's the really wild part. When you calculate how much energy is bound up in the matter in your body, when you apply E equals mc to yourself, you discover that you contain the energy equivalent of multiple nuclear bombs. You are a massive amount of energy that somehow becomes stable and coherent enough to walk around, think, and watch YouTube videos. You're not made of matter that has energy. You're made of energy that's pretending to be matter. And this raises an incredible question. How does energy become matter? What causes light to freeze into the stable patterns we call atoms? Why does some energy stay as light, zipping through space at the speed of light, while other energy becomes matter, moving slowly and experiencing time? The answer might be loops. The answer might be that matter is light that's trapped in a self-sustaining pattern, light chasing its own tail so fast and so perfectly that it appears solid. Let me tell you something that's going to sound completely insane. Empty space isn't empty. The vacuum of space, the nothingness between stars, between atoms, between everything, is actually roiling with activity. It's like an ocean that's invisible and everywhere, and the particles we call matter are just disturbances, waves, loops in this ocean. This is quantum field theory, and it's the most accurate description of reality we've ever developed. Here's how it works. Imagine the entire universe is filled with fields, invisible, intangible fields that permeate everything. There's an electron field, a quark field, a photon field, a field for every type of particle. These fields exist everywhere, at all times, filling all of space. Now, what we call particles are actually excitations in these fields. They're ripples, waves, vibrations in the underlying field. An electron isn't a little ball floating through space. It's a localized disturbance in the electron field. A photon is a ripple in the electromagnetic field. It's like how a wave isn't a separate thing from the ocean. It's the ocean doing something. Think of it like this. Imagine the whole universe is filled with an invisible jello. A particle is like pressing your finger into the jello. You create a dent, a localized disturbance. That dent can move through the jello. It can interact with other dents, but it's not separate from the jello. It is the jello, just configured in a specific pattern. In 1948, physicists figured out something shocking about these fields. Even when there are no particles, even in empty space, the fields are never still. They're constantly fluctuating, creating temporary particles that pop into existence and immediately annihilate, only to pop into existence again. These are called quantum fluctuations or virtual particles. This sounds like science fiction, but it's measurably real. In 1947, physicists Willis Lamb and Robert Rutherford discovered that these quantum fluctuations actually affect real electrons and atoms. They cause tiny shifts in electron energy levels that we can measure. This is called the Lamb shift, and it proved that the vacuum isn't empty. It's bubbling with activity. Even wilder. In 1948, Dutch physicist Hendrik Casimir predicted that if you put two metal plates very close together in a vacuum, they should attract each other because the quantum fluctuations between the plates are restricted compared to the fluctuations outside the plates. This creates a pressure difference. The vacuum pushes the plates together. This is called the Casimir effect, and it was confirmed experimentally in 1997. Empty space pushes things together because it's not actually empty. The vacuum is an ocean of potential. It's seething with energy and possibility. And particles, matter, might just be stable patterns, persistent waves in this ocean. Now here's where this connects to our light loop idea. In quantum field theory, what we call particles are actually excitations that have certain properties: mass, charge, spin. But these properties emerge from the way the field is disturbed. It's like how a wave can have different shapes, heights, frequencies. The wave itself isn't a separate thing. It's a configuration of the water. What if matter particles, electrons, quarks, the things that make up atoms, are just configurations of the electromagnetic field? What if they're patterns where energy has looped back on itself, creating stable, self-sustaining vibrations? In 1927, Paul Dirac developed an equation describing electrons that combined quantum mechanics with Einstein's relativity. And his equation predicted something absolutely bizarre. It predicted that for every particle, there should be an antiparticle, a mirror image with opposite properties. For the electron, there should be a positron with positive charge instead of negative. 4 years later, in 1932, Carl Anderson discovered the positron in cosmic rays. Dirac's equation was right. Antimatter exists. But here's the thing. When a particle meets its antiparticle, when an electron meets a positron, they annihilate and become pure light, 2 photons. The matter disappears and becomes electromagnetic radiation. And the reverse can happen. Photons can become particle-antiparticle pairs. Matter and light are transforming into each other, back and forth. It's like ice melting into water and water freezing into ice. Same substance, different configurations. So maybe, just maybe, an electron is a photon that's somehow trapped in a loop. A photon that's following a path that curves back on itself so perfectly that it becomes stable, persistent, and appears to us as a particle of matter with mass. All right, now we're going deep. We're going to talk about string theory, and I promise to make this make sense, even though it's probably the most abstract, mathematically complex theory in physics. Here's the basic idea of string theory. What if the fundamental building blocks of reality aren't particles at all? What if at the deepest level, everything is made of tiny, vibrating loops of energy? Strings, like little rubber bands, but unimaginably small, about 10 meters. That's 100 billion times smaller than an atom. In string theory, an electron isn't a point particle. It's a string vibrating in a specific pattern. A quark is a string vibrating differently. A photon is yet another vibration pattern. Different particles are different notes on the same cosmic instrument. Think of it like this. A guitar string can vibrate in different ways to produce different notes. The same string creates different sounds depending on how it vibrates. String theory says that reality works the same way. There's one fundamental entity, strings, and all the different particles we observe are just different vibration patterns of these strings. Now, here's where it gets mind-blowing. Many versions of string theory propose that these strings are closed loops. Not open strands, but circles, loops. The fundamental constituents of reality are loops of energy vibrating in complex patterns. String theory was initially developed in the 1960s and 70s, but it really took off in 1984 during what physicists call the superstring revolution, when Michael Green and John Schwarz proved that string theory could be mathematically consistent and might actually describe our universe. Here's why this is relevant to our question about light loops. In string theory, there's no fundamental distinction between matter particles and force-carrying particles like photons. They're all strings vibrating differently. A photon is a certain vibration pattern. An electron is another pattern. But they're made of the same underlying stuff, vibrating loops of energy. This means that at the deepest level, light and matter aren't different types of things. They're different configurations of the same fundamental loops. But string theory goes further. In 1995, physicist Edward Witten made a discovery that unified different versions of string theory into something called M-theory. And M-theory suggests that strings themselves might be different aspects of even deeper structures, brains, membranes of energy existing in higher dimensions. Now I know this sounds crazy, but stay with me, because here's the connection. If fundamental reality is loops of energy vibrating in higher dimensional space, and if particles are manifestations of these vibrations, then everything, absolutely everything, is patterns of energy configured in loops. Your atoms are loops within loops within loops. It's loops all the way down. Here's a mind-blowing implication. In string theory, mass, the property that makes matter feel solid and substantial, isn't some inherent stuff that particles have. Mass emerges from how the strings vibrate. Faster, more energetic vibrations in certain patterns create what we perceive as mass. Slower, different patterns create what we perceive as massless photons. Mass is just a property that emerges from patterns of energy. It's not a substance, it's a behavior. It's how energy acts when it's configured in certain loops. Think about that. The solidity of this world, the fact that you can't put your hand through a table, the weight of your body, the mass of the earth, all of it might emerge from patterns of vibration in tiny loops of energy. There's no stuff at the bottom. It's patterns all the way down. Patterns, creating the illusion of substance. And here's something that will really bake your noodle. String theory requires extra dimensions, not just the 3 dimensions of space and 1 of time that we experience, but up to 11 dimensions total. Where are these extra dimensions? They might be curled up, compactified into tiny loops at every point in space. Even space itself might be made of loops. The very fabric of reality might be loops within loops within loops, with everything. Matter, energy, force, space, time emerging from how these loops vibrate and interact. Let's take a step back and ask a fundamental question. Why does light move? Why does a photon travel at the speed of light, while particles with mass can't reach that speed? Understanding this will help us understand how light could become trapped into matter. Here's something profound that most people don't know. From a photon's perspective, it doesn't experience any time at all. The moment it's created and the moment it's absorbed are the same instant. If a photon could have thoughts, it would experience its entire journey, even if that journey takes billions of years from our perspective, as happening instantaneously. This is because of Einstein's relativity. As you approach the speed of light, time slows down. At the speed of light, time stops entirely. A photon exists in an eternal now. But here's the question. Why does light move at all? Why doesn't it just sit still? The answer is profound. Light has no choice. A photon has 0 mass, and in the mathematics of relativity, anything with 0 mass must move at the speed of light. It cannot be stationary. It's forbidden by the structure of spacetime itself. Think of it like this. Imagine spacetime is like a sheet that's tilted in a direction we can't see, a direction that's neither space nor time, but something else. Particles with mass can grip this sheet because mass curves spacetime around them. They can be at rest because their mass allows them to maintain a position. But a photon has no mass. It can't grip the sheet. It slides down this hidden slope at exactly the speed of light, always moving, never able to stop. Light doesn't move through space over time. Light moves through spacetime, a 4-dimensional structure where space and time are unified. And the speed of light isn't really a speed. It's more like the exchange rate between space and time. It's the conversion factor in the structure of reality itself. Now here's where this gets interesting for our loop idea. What if an electron, a particle with mass, is a photon that's somehow been trapped in a loop? What if it's light that's following a path that curves back on itself in extra dimensions we can't see? If a photon is traveling in a straight line through our 3 dimensions, it has no mass and moves at light speed. But what if that photon is also moving in a tight circle through extra dimensions? What if it's tracing a loop in a higher dimensional space, like a marble rolling around the rim of a bowl? From our perspective in 3 dimensions, we'd only see the particle's motion through our space. The looping motion through the extra dimensions would appear to us as mass, as resistance to acceleration, as gravitational attraction. The photon wouldn't appear to be moving at light speed through our dimensions because most of its motion is in the loop, in dimensions we can't perceive. This idea was actually proposed in 1921 by mathematician Theodor Kaluza and physicist Oscar Klein. They suggested that if there's a hidden fifth dimension curled up into tiny circles, then particles moving through this dimension would appear to us as charged particles with mass. An electron might be light spiraling through an extra dimension. Their theory had problems and wasn't fully correct, but the core insight was brilliant. Motion through hidden dimensions could appear to us as mass and charge. A photon loop through extra dimensions could look like an electron. And this explains something profound. Why can't particles with mass reach the speed of light? Because they're already moving at the speed of light. But some of that motion is through dimensions we can't see, wrapped up in internal loops. From our perspective, they move slower than light, but in the full higher dimensional reality, they're moving at exactly light speed. The motion is just distributed between our visible dimensions and hidden ones. You are moving at the speed of light right now. Every particle in your body is moving at light speed. You just can't see the full path, because most of it is in loops through dimensions beyond our perception. Now I'm going to tell you about one of the strangest properties in all of physics, quantum spin. And understanding spin is crucial to understanding how particles could be loops of light, because spin is evidence that particles aren't simple points. They have internal structure, internal motion. Every particle has a property called spin. Electrons have spin. Quarks have spin. Even photons have spin. When physicists first discovered this property, they thought maybe the particles were literally spinning, rotating like little tops. But then they did the math, and they discovered something impossible. If an electron was actually a spinning sphere, the surface would have to be moving faster than the speed of light. Way faster. That's impossible. Nothing can move faster than light. But electrons definitely have this property we call spin. We can measure it. It has real effects. So what is spin if it's not actual rotation? Here's the truth. Spin is intrinsic angular momentum. Angular momentum is the quantity associated with rotational motion. A spinning ice skater has angular momentum. A planet orbiting a star has angular momentum. And particles have angular momentum even when they're not moving, even when they're at rest. It's like they have rotation built into their existence. They're spinning in a way that doesn't involve moving through space. Think about that. Particles have rotation without actually rotating. They have internal circulation without any circulating parts. How is this possible? Well, if particles are actually excitations in quantum fields, if they're patterns of energy rather than little balls, then spin could be a property of how that pattern is configured. It could be like a whirlpool that has circulation, even though the water isn't a solid object. The circulation is in how the field is disturbed. But here's what really blows my mind. In 1928, Paul Dirac's equation showed that spin is deeply connected to the wave nature of particles. When you treat particles as waves propagating through spacetime, spin emerges naturally from the mathematics. It's not added on. It's built into what it means to be a quantum wave. And here's the kicker. Spin is quantized. It comes in discrete units. An electron always has exactly 1/2 unit of spin. We call this spin 1/2. A photon always has exactly 1 unit of spin, spin 1. You never find an electron with 0.6 units of spin or 1.3 units. It's always exact values. Why? Because of loops. Just like de Broglie showed that electrons can only exist in certain orbits, where their wave connects with itself perfectly, spin can only have certain values where the internal pattern is self-consistent. Imagine a loop of rope. If you twist the rope as you form the loop, you can make a configuration with 1 twist, or 2 twists, or 3 twists. But you can't make a configuration with 1.5 twists. It wouldn't close properly. The number of twists is quantized by the topology of the loop. Particle spin might work the same way. If a particle is a loop of energy in higher dimensions, the amount of twist or circulation in that loop is restricted to values where the pattern is self-consistent. Half-integer spin, These might be the allowed configurations of twisted loops. And different types of particles have different spins. Particles that make up matter, electrons, quarks, neutrinos, all have half-integer spin. We call these fermions. Particles that carry forces, photons, gluons, the hypothetical graviton, all have integer spin. We call these bosons. This isn't a coincidence. In 1940, Wolfgang Pauli proved what's called the spin statistics theorem, which connects spin to how particles behave. Particles with half-integer spin, fermions, obey the Pauli exclusion principle. No two can be in the same state. This is why electrons form shells around atoms, instead of all collapsing into the nucleus. This is why matter is stable. Particles with integer spin, bosons, don't obey the exclusion principle. Multiple bosons can pile into the same state. This is why you can have bright light, many photons all doing the same thing. So spin determines whether you get matter or force, whether you get substance or radiation, whether you get the thing that makes your body solid or the thing that makes light shine. And it all comes down to how the loop is twisted. Matter particles are loops with a half twist. Force particles are loops without that half twist. The entire distinction between matter and energy might just be topology, the geometry of loops. Your body is made of twisted loops. Light is made of untwisted loops. And the twist makes all the difference between being solid and being radiance. Okay, let's pause for a moment, because I know your brain is probably hurting right now. We've covered a lot, and we're not even halfway through. So let me tell you what we're going to explore in the second half, because it gets even wilder. We've established that energy and matter are interchangeable. We've seen that particles behave like waves, forming loops. We've explored quantum fields where particles are disturbances in an underlying ocean of energy. We've touched on string theory, where everything is vibrating loops. And we've seen how particle spin might be evidence of twisted internal structure. But here's what we haven't addressed yet. If atoms are really just light in loops, then what about the structure of atoms? What about the nucleus, the protons and neutrons at the center? What about the strong nuclear force holding them together? What about the fact that we can see atoms with electron microscopes? And most importantly, if you're made of light loops, why do you feel solid? Why does matter resist you? Why can't you walk through walls? The answers to these questions are going to be even more mind-bending than what we've covered so far. We're going to dive into the heart of atoms. We're going to explore why emptiness feels solid. We're going to talk about what mass actually is at the deepest level. And we're going to discuss what this means for consciousness, for identity, for the very nature of existence. Before we continue, hit that subscribe button if you haven't already, because we're about to go deeper than most physics channels ever dare to go. And comment below, what's been the most mind-blowing thing you've learned so far? Is it that you're moving at light speed through hidden dimensions? That mass might just be twisted loops? That the vacuum isn't empty? Also, I want to know, are you understanding this? Should I slow down? Speed up? Let me know, because I want this to click for everyone watching. All right, let's dive into the structure of atoms themselves and see how deep this rabbit hole really goes. We've been talking about electrons, the particles that orbit the nucleus of an atom. But what about the nucleus itself? That's where most of an atom's mass resides. That's the heavy core made of protons and neutrons. If electrons might be loops of light, what about these nuclear particles? Here's something that will surprise you. Protons and neutrons aren't fundamental particles. They're composite. They're made of smaller particles called quarks, held together by particles called gluons. And this is where things get really interesting. In 1968, physicists at Stanford performed deep inelastic scattering experiments where they fired high-energy electrons at protons. They expected the electrons to bounce off the protons like marbles bouncing off other marbles. But instead, they saw something weird. The electrons were scattering off smaller things inside the protons. They had discovered quarks. A proton contains 3 quarks, 2 up quarks, and 1 down quark. A neutron contains 1 up quark and 2 down quarks. These quarks are held together by gluons, which are the carriers of the strong nuclear force. Now here's the absolutely mind-blowing part. When physicists calculated how much mass the quarks themselves have, they got a shocking answer. The 3 quarks in a proton, if you added up their masses, only account for about 1 to 2% of the proton's mass. Think about that. The proton has 100 units of mass, but the quarks inside it only have 1 or 2 units of mass. Where does the other 98 to 99% come from? It comes from energy. Specifically, it comes from the kinetic energy of the quarks as they zoom around inside the proton, and from the energy of the gluon field binding them together. The quarks are moving at nearly the speed of light inside the proton, and all that motion, all that kinetic energy, contributes to the proton's mass through E equals mc. But it gets weirder. Gluons are like photons. They're massless particles, pure energy. And the strong force that gluons carry has a bizarre property. It gets stronger the farther apart quarks get. It's like a rubber band. Stretch it, and it pulls back harder. In fact, if you try to pull quarks apart, you put so much energy into the gluon field that the field spontaneously creates new quarks out of that energy. You can never isolate a single quark. They're permanently confined inside composite particles. So a proton or neutron is like a bag of churning energy. 3 quarks racing around near light speed, connected by gluons that are constantly appearing and disappearing, with virtual quark-antiquark pairs popping into and out of existence from the seething energy. The interior of a proton is chaos, a storm of particles and energy that somehow maintains a stable overall structure. And here's the thing. Quarks also have spin and charge, and all the other properties we associate with fundamental particles. But in quantum field theory, quarks are excitations in the quark field, just like electrons are excitations in the electron field, and photons are excitations in the electromagnetic field. And in string theory, quarks are just strings vibrating in a different pattern than electrons or photons. So if we follow the logic all the way down, atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. Quarks and gluons are excitations in quantum fields. And those excitations might be loops of energy vibrating in higher dimensional space. It's loops within loops within loops. At every level, energy configured into self-sustaining patterns, creating the illusion of substance. And almost all the mass in your body, 98 to 99% of it, doesn't come from the intrinsic mass of fundamental particles. It comes from energy, from motion, from fields, from the kinetic and potential energy locked inside atomic nuclei. You are mostly energy pretending to be mass. You are motion masquerading as substance. You are light and force fields dressed up as matter. But wait, what about that 1 to 2% of mass that is intrinsic to particles like quarks and electrons? Where does that come from? Why do particles have mass at all? This is one of the deepest questions in physics, and the answer involves the most important discovery of the 21st century so far. In 1964, physicist Peter Higgs, along with several others, proposed that the universe is permeated by a field, the Higgs field, that gives particles their mass. This sounds weird, so let me explain. Remember how I said the universe is filled with quantum fields for every particle? Well, the Higgs field is another field, but it has a special property. Unlike most fields, which have 0 value in their ground state, the Higgs field has a non-zero value everywhere. Even in empty space, the Higgs field has a constant non-zero value. It's like the universe has a baseline level of Higgsness everywhere. Now, particles get their mass by interacting with the Higgs field. Think of it like this. Imagine you're walking through air, there's barely any resistance. Now imagine walking through water, more resistance. Now imagine walking through honey, lots of resistance. The medium you're moving through determines how hard it is to move. The Higgs field is like a cosmic medium that permeates everything. Particles that interact strongly with the Higgs field experience lots of drag. They're hard to accelerate, hard to move. We interpret this drag as mass. Particles that barely interact with the Higgs field experience little drag. They have little mass. Particles that don't interact at all with the Higgs field, like photons, experience zero drag. They have zero mass and must move at light speed. Mass is resistance to acceleration. And that resistance comes from dragging through the Higgs field that fills all of space. In 2012, scientists at the Large Hadron Collider discovered the Higgs boson, the particle that's in excitation in the Higgs field. This discovery confirmed that the Higgs field exists and is responsible for giving particles their mass. Peter Higgs and Francois Englert won the Nobel Prize in 2013 for predicting this field almost 50 years earlier. But here's the really profound part. The Higgs field gives particles their intrinsic mass, but it doesn't care what particles are made of. It doesn't matter if you think particles are little balls, or waves, or strings, or loops. The Higgs field interacts with excitations in other fields, giving those excitations the property we call mass. So even if particles are loops of light, those loops interact with the Higgs field, and that interaction makes them behave as though they have mass. The loops get sticky. They resist acceleration because they're constantly interacting with this cosmic field. Think about this. The reason you have weight, the reason you can't accelerate to light speed, the reason matter feels substantial. All of it comes from invisible fields that permeate space. You're not heavy because you're made of heavy stuff. You're heavy because you're made of patterns that interact strongly with an invisible cosmic medium. And the Higgs field itself is just another quantum field. It's the same type of thing as the electromagnetic field or the electron field. It's a mathematical structure that permeates space, and excitations in it create the Higgs boson. So reality is layers of invisible fields, all interacting with each other, creating excitations that we perceive as particles, with those particles having properties like mass and charge based on how they interact with various fields. And if particles are actually loops of energy in higher dimensions, then mass is what happens when those loops interact with the Higgs field. The loops slow down, become heavy, become trapped in our three-dimensional space rather than zipping through it at light speed. An electron is light that got stuck in the cosmic honey of the Higgs field. A quark is light that got really stuck. A photon is light that didn't get stuck at all. And you are a complex dance of loops that are all stuck in varying degrees, creating the patterns of stability and structure that allow you to exist as a coherent entity over time. Okay, so we've established that particles might be loops of energy, that mass comes from interaction with the Higgs field, and that most of an atom's mass comes from energy inside the nucleus. But this raises a crucial question. If atoms are mostly empty space, if particles are just energy patterns, if there's no actual stuff, then why does the world feel solid? Why can't you walk through walls? Why does your chair support you? Why does anything feel real and substantial? Here's the shocking truth. You've never actually touched anything in your entire life. When you think you're touching something, when you feel the surface of a table or hold someone's hand, what you're actually experiencing is electromagnetic repulsion between the electrons in your atoms and the electrons in the other object's atoms. Electrons repel each other because they have the same charge. When your hand gets close to a table, the electrons in your hand and the electrons in the table push against each other. They never actually touch. They just get close enough that their electromagnetic fields strongly repel. And your brain interprets this repulsion as the sensation of touch. Think of it like two magnets with the same poles facing each other. They push apart without touching. That's what's happening at the atomic level when you touch things. You're feeling magnetic repulsion between charged particles. The solidity of matter is electromagnetic force. It's light, because the electromagnetic force is carried by photons, the particles of light. When electrons repel, they're exchanging virtual photons. They're communicating through light. So when you touch something, you're experiencing light. Particles of light passing between electrons, creating a repulsive force that your brain interprets as solidity. In 1947, physicists Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed quantum electrodynamics, QED, which describes exactly how charged particles interact through the electromagnetic force. And it describes this interaction as the exchange of virtual photons. Every force you've ever felt, every push, every touch, every sensation of substance has been mediated by photons, by light. Now here's something even deeper. The reason atoms don't collapse is the Pauli exclusion principle, which says that two electrons can't be in the same quantum state. This is why electron shells form around atoms. This is why your hand doesn't pass through the table. The electrons can't occupy the same space and states, so they repel. But the exclusion principle is a consequence of spin, specifically half-integer spin. It emerges from the mathematics of quantum fields. And as we discussed, spin might be evidence of particles being twisted loops. So the solidity of matter, the fact that things take up space and resist interpenetration, comes from the topology of loops. It comes from how energy patterns can or cannot overlap. And there's even more. Atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be like a marble at the center, and the electrons would be like tiny gnats buzzing around the outer edges. Everything in between is empty. Your body is 99.99999% empty space. You are almost entirely nothing. The tiny fraction that isn't empty is just energy patterns, loops in quantum fields. And even the empty space isn't truly empty. It's filled with quantum fields and virtual particles constantly appearing and disappearing. So when you feel the solidity of your body, when you feel weight and substance, what are you actually feeling? You're feeling electromagnetic forces. You're feeling the exclusion principle. You're feeling quantum fields interacting. There is no stuff. There never was. There's just patterns of energy creating forces, and your brain interpreting those forces as a material world. The world is a hologram made of fields and forces, and you are too. You are an electromagnetic sculpture, a pattern held together by light. Now we need to address something that's been lurking beneath everything we've discussed: the observer effect and the measurement problem in quantum mechanics. Because if particles are really waves and loops of energy, then what happens when you look at them? What happens when you measure them? This is where quantum mechanics gets truly strange. Here's the basic issue. When you're not observing a particle, it exists in a superposition of states. It's in multiple states at once. An electron can be in multiple positions at once. A photon can take multiple paths at once. The particle is described by a wave function that spreads out over space, representing all the possible states it could be in. But when you measure the particle, when you observe it, the wave function collapses. Suddenly, the particle is in one definite state, one definite position. All the other possibilities vanish. This was demonstrated in that famous double-slit experiment we mentioned earlier. When you're not watching which slit a particle goes through, it goes through both slits at once and creates an interference pattern. But the moment you set up a detector to see which slit it goes through, the interference pattern disappears. The particle goes through one slit or the other, not both. Observation changes the behavior of particles. Measurement forces them to choose a state. Why? Nobody knows for sure. This is the measurement problem, and it's been argued about for almost 100 years. In 1927, Werner Heisenberg proposed that measurement disturbs the system, like shining light on an electron to see where it is, which changes its momentum. But later physicists realized it's deeper than that. Even in theory, even if you could measure perfectly without disturbing anything, the wave function would still collapse. It's not just about practical disturbance. It's something fundamental about the nature of quantum systems and observation. Niels Bohr argued that particles don't have definite properties until they're measured. The properties literally don't exist beforehand. Asking, where was the electron before I measured it, is meaningless. It wasn't anywhere. It was in a superposition of being in many places, and measurement creates the reality of it being in one place. Einstein hated this idea. He famously said, "I like to think the moon is there even when I'm not looking at it." He believed particles have definite properties at all times, and quantum mechanics is just incomplete. There are hidden variables we don't know about that determine outcomes. But in 1964, physicist John Bell proved that if hidden variables exist, they would have to behave in very weird ways. They'd have to be non-local, meaning they'd have to affect things faster than light. And experiments by Alling Aspect in the 1980s, and many others since, have confirmed quantum mechanics is right. Nature really is fundamentally probabilistic. Particles really don't have definite states until measurement. Now here's where this connects to our loop idea. If particles are loops of energy, waves in quantum fields, then when they're not being measured, the loops are smeared out. They're not in one place. They're probability clouds, existing in superposition across space. But measurement causes the wave function to collapse. The loop suddenly becomes localized. The energy pattern crystallizes into a definite configuration. What causes this? One interpretation is that consciousness plays a role, that observation by a conscious mind collapses the wave function. This was suggested by physicists like Eugene Wigner and John von Neumann. But this seems bizarre and leads to all sorts of philosophical problems. Another interpretation, proposed by Hugh Everett in 1957, is the many worlds interpretation. The wave function never collapses. Instead, every measurement causes the universe to split into multiple branches, one for each possible outcome. In one branch, the particle is here. In another branch, it's there. All possibilities are realized in different parallel universes. This sounds like science fiction, but many physicists take it seriously because it solves the measurement problem without requiring any special collapse mechanism. A third interpretation, called decoherence, suggests that when a quantum system interacts with the environment, with air molecules, photons, other particles, the different parts of the superposition get entangled with the environment in different ways. From our perspective, it looks like collapse because we can only see the part of the system that's consistent with the environment we're in. But here's what I want you to understand. Whatever interpretation you prefer, the fundamental fact is that particles aren't real in the way we normally think. They're not little definite objects existing in definite states. They're clouds of possibility, waves of potential that only crystallize into definite states through interaction and measurement. And if particles are loops of light in higher dimensions, then those loops are ghostly, probabilistic, smeared across space and time, until something, observation, interaction, entanglement with environment, pins them down into the definite patterns we call particles. Reality is not solid. Reality is fluid, probabilistic, undefined until the moment it's observed. You are both observer and observed, both the looker and the looked at, both the measurer and the measured. And in some sense, you are creating the definite world around you simply by interacting with it. Let's go even deeper. If atoms are loops in spacetime, if matter is energy curved back on itself through space and time, then we need to talk about the nature of time itself. Because time is way weirder than you think, and it's intimately connected to this idea of loops. Here's a question. Does the past still exist? Does the future already exist? Or is only the present moment real, with past gone and future yet to come. Our everyday experience says only the present is real, the past is memories, the future is possibilities. But Einstein's relativity says something radically different. According to relativity, all moments in time are equally real. The past, present, and future all exist simultaneously. The universe is a four-dimensional block, the block universe, where time is just another dimension like space. Think of it like a movie on a DVD. The entire movie exists all at once on the disc. The beginning, middle, and end are all there. You experience them sequentially as you watch, but they all exist simultaneously as data on the disc. Einstein's relativity says the universe is like that. All moments exist simultaneously in the four-dimensional structure of spacetime. In 1905, Einstein showed that simultaneity is relative. Events that appear simultaneous to one observer don't appear simultaneous to another observer moving at a different speed. There's no universal, now that everyone agrees on. Your present moment includes events that are in the past or future for someone else moving relative to you. This only makes sense if all moments of time exist equally. If the past and future are as real as the present, just located at different positions in the fourth dimension. Now here's where this connects to particles being loops. If all moments of time exist simultaneously, then a particle's world line, its path through spacetime, is a complete, timeless object. An electron isn't something that exists at one moment, and then the next moment, and then the next. The electron is a curve through spacetime, a four-dimensional worm connecting past to future. And if particles are loops of energy, then in the block universe picture, they're loops through spacetime. They're closed curves in four dimensions, not just three. In fact, there's an interpretation of antiparticles that suggests this. Physicists John Wheeler and Richard Feynman proposed in the 1940s that an antiparticle is a particle moving backward in time. When you see an electron-positron pair creation, you're actually seeing one electron that goes forward in time, then loops back and goes backward in time. The positron is the electron's past self. This sounds insane, but it actually works mathematically. In Feynman diagrams, the pictorial way physicists describe particle interactions, you literally draw antiparticles as particles going backward in time. So a particle's existence might be a loop through time itself. It goes forward, then back, then forward again, creating intricate patterns through the four-dimensional fabric of spacetime. From outside time, from a perspective that sees all moments at once, you would see particles as elaborate knots in spacetime, loops within loops, curves doubling back on themselves, creating the illusion of multiple particles when it might all be one particle tracing an incredibly complex path. Now, you might be thinking, if all moments exist equally, if the future is already determined, then where's free will? Are we just watching a movie that's already been filmed? This is a deep philosophical question. Some physicists argue that the block universe is compatible with free will, that your choices are part of the four-dimensional structure, that you're not watching the movie, but are the movie. Others argue that it's deterministic and free will is an illusion. But here's something to consider. Quantum mechanics introduces true randomness. Measurements have genuinely random outcomes that cannot be predicted even in principle. So maybe the block universe isn't completely determined. Maybe it has branches, multiple possible futures, and your choices in quantum randomness select which branch you experience. Or maybe, in the many worlds interpretation, all branches exist. Every choice you could make, you do make in different branches of the universe. You're not one path through spacetime, but an ever-branching tree of paths. Either way, the key insight is this: time is not what it seems. You experience life as a sequence of moments, but underlying that experience might be a timeless four-dimensional structure where your entire life, past, present, and future, exists as a complete pattern. And the particles you're made of, might be loops through this four-dimensional space. Curves of energy that trace paths forward and backward through time, creating the intricate dance we perceive as matter. You are not just in the universe. You are a pattern woven into the universe's four-dimensional tapestry. You are a loop in the fabric of space-time itself. Now let's talk about something that's going to tie all of this together in an unexpected way: information. Because at the deepest level, reality might not be energy or matter or even loops. It might be information. In 1948, mathematician Claude Shannon developed information theory, which mathematically defines what information is. Information is basically the resolution of uncertainty. When you learn something new, when uncertainty is reduced, that's information. Now here's something profound. Information has a deep connection to entropy. Entropy is usually thought of as disorder or randomness, but more precisely, it's the number of possible microscopic states a system could be in. High entropy means many possible states. High uncertainty. Low entropy means few possible states, low uncertainty. So entropy is related to information. A high entropy system contains little information because it could be in many states. You don't know much about it. A low entropy system contains lots of information because it can only be in a few states. You know a lot about it. In the 1970s, physicist Stephen Hawking made an astonishing discovery about black holes. They have entropy. Specifically, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is weird because we usually think of entropy as depending on how much stuff you have, the volume. But for black holes, it depends on the surface area. This led physicists Jacob Bekenstein and later Leonard Susskind and Gerard T. Hooft to propose the holographic principle, the idea that all the information contained in a volume of space can be represented by information on the boundary of that space. The three-dimensional universe might be encoded on a two-dimensional surface, like a hologram. Think of it like this. You know those 3D holograms where a 2D image contains information that creates a 3D picture when you look at it, right? The holographic principle says the whole universe might work that way. The three-dimensional space we experience might be a projection of information encoded on a two-dimensional cosmic horizon. This sounds like philosophy, but it's serious physics. In 1997, Juan Maldacena proved a version of this in string theory called the ADS-CFT correspondence. He showed that a certain type of universe with gravity in its interior is mathematically equivalent to a quantum field theory without gravity on its boundary. The interior and boundary are different descriptions of the same thing. Now, what does this have to do with loops of light? Well, if reality is fundamentally information, and if that information can be encoded on surfaces, then particles, loops of energy, might be ways that information is stored and processed in the structure of spacetime. A particle's properties, its mass, charge, spin, position, are all information. And if particles are loops, then loops are information storage devices. They're bits of cosmic data encoded in the geometry of spacetime. Here's where it gets really wild. Physicist John Wheeler, one of the giants of 20th century physics, proposed the it from bit, that physical reality, it emerges from information, bit. He suggested that at the deepest level, the universe is made of information, and matter and energy are manifestations of that information. In 2001, physicist Seth Lloyd calculated that the universe is, in a sense, a quantum computer. All the particles and interactions are constantly performing computations, processing information. You right now are a computation happening in the quantum substrate of reality. And if particles are loops of light, then you are loops of light processing information about themselves. You are light that has become so complex, so intricately looped and patterned, that it has become aware. You are the universe computing itself, understanding itself, experiencing itself. Every thought you have is information processing in patterns of energy. Your consciousness is a vast computation performed by countless quantum interactions in your brain. And your brain is made of atoms, which are loops of light, which are patterns in quantum fields, which are information structures. You are information that has learned to feel. You are data that has become conscious. You are the universe's way of knowing itself. Now, entropy has been increasing since the Big Bang. The universe has been spreading out, cooling down, becoming more disordered. This is the second law of thermodynamics. Entropy always increases. But here's something beautiful. Locally, in certain places, complexity can increase. Structures can form. Life can emerge. You are an island of complexity in a sea of entropy. You are a temporary decrease in local disorder, maintained by constantly processing energy and information. You are a loop in the flow of entropy, an eddy in the stream, a pattern that persists for a while before dissolving back into the cosmic soup. But while you exist, while you maintain your pattern, you are processing information at a staggering rate. Your brain contains about 86 billion neurons, each connected to thousands of others, all firing in intricate patterns. You are one of the most complex information processing systems in the known universe. And you're made of light. Loops of light so intricate, so beautifully organized, that they can contemplate their own existence. Now let's bring this home. Let's talk about what this means for you, personally, right now, as you watch this video. You started this video thinking you were a solid object, a body made of meat and bone, sitting in a room, watching a screen. But now you know differently. You are not solid. You are mostly empty space minus 99.9999999% empty. The tiny fraction that isn't empty is energy patterns in quantum fields. Loops of light interacting with the Higgs field, creating the illusion of mass. Particles that are really waves, smeared across space in probability clouds until observation pins them down. The atoms in your body weren't created here on Earth. They were forged in the hearts of stars billions of years ago. Every carbon atom in your body came from a star that lived, fused lighter elements into carbon, and then exploded, scattering those atoms across space. Every heavier atom, the iron in your blood, the calcium in your bones, came from even more violent stellar deaths, from supernovae that briefly outshone entire galaxies. You are literally made of stardust. But more than that, you're made of starlight. Because those atoms are loops of light that were created in the intense energy of stellar fusion and supernova explosions. The hydrogen in your body, which makes up about 60% of your atoms, was created in the Big Bang itself, 13.8 billion years ago. Those hydrogen atoms have been around since the beginning of the universe, cycling through countless stars and planets and life forms before becoming part of you. You are 13.8 billion years old. Parts of you. Anyway, you are recycled stardust, reconfigured starlight, ancient cosmic energy temporarily organized into the pattern that calls itself you. And here's something that should blow your mind. The atoms in your body are constantly being replaced. You breathe in atoms, eat atoms, drink atoms. You breathe out atoms, excrete atoms, shed skin cells. The atoms you're made of today are not the same atoms you were made of 7 years ago. Almost every atom gets replaced over time. So what are you? You're not the atoms. You can't be, because those atoms change. You're the pattern. You're the information. You're the way the atoms are organized. You are a persistent pattern in the flow of matter and energy. You are a wave in the ocean of atoms, maintaining your shape even as the water that forms you constantly flows through and is replaced. And consciousness? Your sense of self, your inner experience, your feeling of being you, that emerges from the pattern. It's not located in any one atom or neuron. It's a property of how everything is organized and interacting. In a sense, you are what it feels like to be a certain type of pattern, a pattern complex enough to model itself, to be aware of itself, to contemplate its own existence. You are the universe experiencing itself. You are starlight that has become conscious. You are loops of ancient cosmic energy arranged in such an intricate dance that they can wonder about their own nature. And here's the thing that gets me, that fills me with awe every time I think about it. You are improbable. The chances of you existing, of this particular pattern emerging, are astronomically small. Your parents had to meet. Their parents had to meet. Going back through generations, through millions of years of evolution, through billions of years of cosmic history. Every step had to happen just right for you to be here. You are a cosmic lottery jackpot. You are a miracle of probability. You shouldn't exist, but you do. And for a brief moment, 100 years if you're lucky, you get to be aware. You get to know that you're made of stardust. You get to understand that you're loops of light. You get to grasp, however partially, the nature of reality itself. That's precious. That's sacred in a secular, scientific way. You are the universe's way of understanding itself, and that makes you important beyond measure. Now, some people find this reductionist. They say, if I'm just atoms, just energy, just patterns, then where's the meaning? Where's the magic? But I think it's the opposite. Understanding what you really are makes you more magical, not less. You thought you were solid lumps of matter, but you're not. You're intricate dances of energy. You're quantum symphonies. You're space-time doing not theory on itself. You're not less than you thought. You're more. So much more. Every sensation you feel is electromagnetic forces, photons bouncing between atoms. Every thought you think is electrons flowing through neural pathways. Every emotion you experience is chemistry, atoms rearranging, energy flowing, patterns shifting. But those patterns are real. Your experiences are real. Your consciousness is real. It's all made of loops of light, but that doesn't make it less real. It makes it miraculous that light can do this, that energy configured just right can feel, can think, can love. You are proof that the universe can know itself. You are evidence that matter can become mind. You are living testament to the fact that loops of light, given enough time and the right conditions, can become beings that contemplate the nature of loops of light. As we near the end of this journey, let's address the biggest questions that remain. Because while we've covered a lot, there's still so much we don't know. Question 1. If particles are really loops of light or energy, why do we observe so many different types of particles? Why are there electrons and quarks and neutrinos and all the rest? Why not just one type of loop? The answer from string theory and quantum field theory is that different particles are different vibration patterns or different configurations of the same underlying entity. It's like how one string can play different notes, but we don't fully understand why nature chose these particular notes, these particular patterns, why these particles and not others. This is related to the hierarchy problem in physics. Why is gravity so much weaker than the other forces? Why is the Higgs mass what it is? There seem to be fundamental constants and properties that are finely tuned to allow our universe to exist, and we don't know why. Some physicists propose the anthropic principle. We observe these values because if they were different, we wouldn't exist to observe anything. In a multiverse with many different universes having different constants, we necessarily find ourselves in one where the constants allow life. Others hope that a deeper theory, a theory of everything, will explain why the constants must have the values they do. Question 2. What came before the Big Bang? If the universe started 13.8 billion years ago in an incredibly hot, dense state, what was there before that? This might be a meaningless question. Time itself might have started with the Big Bang. Asking what came before time is like asking what's north of the North Pole. The question doesn't make sense. But some theories suggest the Big Bang might have been a bounce, that the universe was contracting, reached a minimum size, and then started expanding. Or that our Big Bang was the result of quantum fluctuations in a larger meta-universe. Or that time is cyclical, with bangs and crunches repeating eternally. We simply don't know. The conditions at the very beginning of the universe were so extreme that our current physics breaks down. We need a theory of quantum gravity to understand it. Question 3. Are there really extra dimensions? Do particles really move through higher dimensional spaces we can't perceive? String theory says yes. There must be extra dimensions for the math to work. But those dimensions are curled up incredibly small, far too small to detect directly with current technology. Some versions of string theory predict effects we might be able to measure, tiny deviations from Einstein's gravity at very small scales, or the production of certain particles in accelerators. So far, no such effects have been found. But absence of evidence isn't evidence of absence. We might just not be looking hard enough yet. Question 4. What is dark matter? Observations of galaxies and galaxy clusters show that there's much more mass present than we can see. Something invisible is providing gravitational pull. We call it dark matter. But what is it? It could be particles that don't interact with light, particles that only feel gravity, and perhaps the weak nuclear force. Many physicists are searching for such particles. Or it could be something weirder, modifications to gravity itself, or effects from extra dimensions. If dark matter is particles, they might be heavier cousins of the particles we know. They might be their own loops of energy, vibrating in patterns that don't couple to the electromagnetic field, and thus don't interact with light. Invisible loops surrounding visible loops. Question 5. What is consciousness? How does subjective experience arise from objective physical processes? This is the hard problem of consciousness, and honestly, we don't know. We know that consciousness correlates with certain brain activity. We know it's complex and involves massive information processing, but we don't know how or why physical processes create subjective experience. Why there's something it's like to be you. Some philosophers argue that consciousness is fundamental, that it's a basic feature of reality alongside mass and charge. Others argue it's an emergent property, something that arises from complex organization without being fundamental. If you're made of loops of light, and consciousness emerges from how those loops are organized, then consciousness might be what it feels like to be a certain type of information processing pattern. But that doesn't fully explain the mystery of subjective experience. Maybe consciousness is the universe observing itself. Maybe, when quantum wave functions collapse due to observation, consciousness is what it feels like to be the thing doing the observing. Maybe you are the universe's way of actualizing quantum possibilities into definite realities. This is speculation, but it's beautiful speculation. Question 6. Is any of this real? Or is it all just mathematical description? Do quantum fields and strings and higher dimensions actually exist? Or are they just useful fictions that help us predict experimental results? This is a question of scientific realism versus instrumentalism. Realists believe that our theories describe real things, that electrons really exist, fields really exist. Instrumentalists believe that theories are just tools for making predictions, that asking if they're real is meaningless. Most physicists are practical realists. They think the entities in our best theories are probably real in some sense, even if we don't fully understand what that sense is. But here's what I believe. Something is real. You exist. The universe exists. The regularities we observe are not arbitrary. And our theories, however imperfect, are getting closer to understanding the deep structure of reality. Maybe particles aren't literally loops of light. Maybe there's something stranger that we approximate as loops. But the core insight, that matter is energy organized in self-sustaining patterns, that's almost certainly true. You are patterns. The world is patterns. And those patterns follow comprehensible laws that we're slowly figuring out. Let me pull everything together now and show you the full picture. We started with a simple question. What if atoms are just light in loops? And we've discovered that this isn't just a poetic metaphor. It's close to how cutting-edge physics actually describes reality. Light and matter are interchangeable. E equals mc. Photons can become particle-antiparticle pairs, and particles can annihilate into photons. They're different states of the same fundamental stuff. Particles behave like waves that loop back on themselves. Electrons in atoms form standing waves. Particle spin suggests internal rotation or circulation. Everything about quantum mechanics points to particles being wave patterns, not solid lumps. Quantum field theory tells us that particles are excitations in fields, ripples in an underlying ocean of energy that permeates all space. The empty vacuum is full of these fields, constantly fluctuating, creating virtual particles. String theory suggests that at the deepest level, particles are vibrating loops, closed strings of energy. Different vibrations create different particles. And these loops might exist in higher dimensional spaces we can't directly perceive. Mass, the property that makes matter feel substantial, comes from two sources: interaction with the Higgs field for fundamental particles, and kinetic energy for composite particles like protons. Either way, mass is energy, not substance. The solidity of matter is electromagnetic repulsion between electrons. When you touch something, you're feeling light. Photons mediating forces between charged particles. You've never actually touched anything. Time might be an illusion of consciousness. The block universe suggests all moments exist simultaneously, with particles being four-dimensional world lines, possibly loops through spacetime itself. Reality might be information at the deepest level. Particles are information storage and processing devices. You are a pattern of information so complex that it has become self-aware. Now, here's the culminating insight, the revelation that ties everything together. You are the universe's way of understanding itself. You are starlight that has become conscious. You are loops of cosmic energy so intricately arranged that they can contemplate their own nature. Every atom in your body was formed in stars. Every force you feel is mediated by light. Every sensation, thought, and emotion is patterns of energy flowing through neural networks made of atoms, made of loops, made of fields, made of math, made of ... We don't know the final answer. Maybe there is no final answer. Maybe it's patterns all the way down, with no ultimate ground. But here's what makes this beautiful rather than nihilistic. You exist. Against all odds, despite the astronomical improbability, you are here. You are a temporary eddy in the flow of entropy, a brief decrease in disorder, a moment when the universe becomes aware of itself. And during your brief existence, you get to know this. You get to understand that you're made of stardust, that you're patterns of light, that you're information processing itself. This knowledge doesn't diminish you. It enlarges you. You're not just a person. You're a piece of the cosmos experiencing itself from this particular perspective. When you look at the stars, you're looking at your birthplace. When you breathe, you're exchanging atoms with the entire biosphere. When you think, you're performing quantum computations that ripple through the fabric of spacetime itself. You are intimately connected to everything. The same quantum fields that make up your body make up the Earth, the Sun, the distant galaxies. You're not separate from the universe. You're a part of it, a pattern within it, a manifestation of it. And love, consciousness, beauty, these aren't separate from the physics. They emerge from it. They're what complex patterns of energy feel like from the inside. The reductionist view says you're nothing but atoms. But atoms are loops of light. Light is excitations in quantum fields. Fields are mathematical structures describing reality. And that reality includes consciousness, love, meaning. You're not nothing but atoms. You're atoms.